This video is intended to give you all the important need-to-know information that you need to decide what's the right starter scope for you. Now, telescopes do two things. They allow you to see faint objects and they allow you to see small objects. Faint objects tend to be outside our solar system and they tend to be big and fuzzy. The so-called deep sky objects, galaxies, globular clusters, nebula, supernova remnants, and so on. The small objects tend to be bright, double stars, star clusters, planets, and so on. Magnification is largely a red herring here. It's basically all about aperture. The ability of a telescope to see faint objects basically goes with the square of the aperture. So that is, if you double the size of the aperture, you get 4 times as many photons, and that allows you to see much fainter objects. The larger the diameter of the telescope, the smaller the object the telescope has the capability to see. But this time it basically goes linearly with the aperture. That is, you double the aperture, then you can see objects about half the size. So where's the problem, I hear you ask? The bigger the scope, the better, right? Well, to a degree, yes. However, there are other limitations on the telescope. The first and most obvious is the sky. All scopes are essentially useless under a cloudy sky. But even if it's not cloudy, the sky is commonly a greater limiting factor than the telescope. If you're looking at faint objects such as nebula, these tend to be big and fuzzy, and so the darkness and the clarity, that's basically how transparent the sky is, are the principal factors. If your sky is murky or has a lot of light pollution or there's even a full moon in the sky, you can largely forget about it. A big scope under those circumstances is just an expensive way of making it hard to look at the stars. Small objects tend to be bright, like planets and double stars, so the clarity of the sky is not terribly important. However, the stability of the atmosphere is crucial. I mean, you know that shimmer you get on a hot road? Well, the moon is about half a degree in size, and a big planet like Jupiter is about 1/60th of the angular size of the moon. And a good scope can, in principle, resolve up to about 60 features across that disk. So as you can imagine, you need a very still atmosphere to fully capitalize on that. The bigger the scope, the stiller you need the atmosphere to be to take full advantage of it. Indeed, for resolution purposes, once the scope gets up to about 30 centimeters or 12 inches in diameter, the atmosphere is essentially never stable enough and always limits the performance of the telescope. So let's assume for the moment that the skies are excellent. The next major factor is ease of use. Most scopes are not permanently set up, and so they have to be moved outside and set up. A scope that weighs as much as a small car might have superb capabilities, but if it takes an hour to move outside and set up, experience has shown that it'll simply tend not to be used. Typically, the largest scope that can be handled by one person is about a 6-inch refractor or a 12-inch reflector type scope. And because telescopes typically deal with resolving such small objects, the telescope's performance is frequently atrociously subpar until it is cooled down to about the outside temperature. And the larger the scope, the longer that takes. It really all depends what sort of astronomy you're going to be into. If you just want a scope that you can take out into the garden and stargaze for half an hour or so, having to set things up and let them cool down for half an hour or so can have a significant deterrent effect. Now, the scopes themselves come in 2 basic forms, those that focus the light by lenses and those that use mirrors. Those that use mirrors typically have a secondary mirror in the optical train, and this obviously reduces the light gathering capability of the telescope and also lowers the resolution. In practical terms, what that means is you get more contrast images out of refractors. But most refractors have the problem that they focus the red light and the blue light in different areas, the so-called achromats. Pragmatically, that means that bright objects like planets get this purple halo that you cannot get rid of. Well, cannot. You can do it by putting extra lenses in the optical train, the so-called apochromatic refractors, but that makes the scopes cost about 10 times as much as an equivalent aperture reflector type scope. Having said that, I have used these scopes under dark skies, and they are almost magically beautiful to use in the way that the stars fall, if you'll excuse the poetic language, into impossibly sharp pinpricks of light on a black velvet sky. Now you need to mount the scope. You see, when you're looking at this very small portion of the sky, first of all, of course, you need a very sturdy mount. That's really important. But secondly, the Earth's rotation becomes a bit of a bitch. The Earth is hammering around such that the sky apparently rotates, well, once per day. And if your scope's not driven to compensate for that rotation, you'll just observe the object you're looking at drift out of the frame depending on the power, but typically in about a minute. The undriven mounts, of course, are much cheaper, but you have to compensate for the Earth's rotation by actually moving the telescope, and that can be a pain. Driven scopes these days are almost exclusively the so-called go-to scopes. Go-to scopes basically require your location on the Earth, the time, and a few star observations such that the scope knows in which direction it's pointing, such that you can drive the mount to track objects. The setup might only take 10 minutes or so, but it's still a pain in the ass, and even more so if you don't have a good idea of what you're doing. However, after that, most scopes will allow you to request an object, which the scope will then intuitively find for you. But if the scope gets nudged or moved, you'll typically have to realign it. Now, the go-to mount can save a lot of time in messing around with star atlases and finders, but it also removes a lot of the organic feel of exploring and getting to know the sky. The scope just pans and tilts, and after that all you do is look into the eyepiece. So these are the basic metrics you need to assess when choosing which scope is right for you. After that, it basically boils down to how much you're willing to spend. If you're looking for a cheap entry-level telescope, I would recommend the biggest Dobssonian. That's essentially an undriven alt-azimuth mounted Newtonian reflector that you can afford. It's the cheapest way to get aperture. Light buckets give you a lot of versatility. They're great for looking at faint objects, and they will give you good views of the planets. However, they're not typically driven, and that means that you have to find the objects yourself and track them yourself. My next choice would probably be an alt-azimuth mounted Schmidt go-to scope. Relatively good value for money in terms of aperture per dollar, and the scopes are driven, which allows potential for astrophotography. For casual stargazing use, and if cost really isn't an issue, I would probably go for a alt-azimuth mounted 4-inch apochromatic type refractor. Fast to set up, beautiful to use, and due to the build quality on the instruments, collimation of the optics is essentially never required. Now, the build quality on scopes these days is all around fairly reproducibly high, but of course this is the internet age, and when you're actually thinking of buying a scope, go to somewhere like Amazon and check out the ratings. After that, the cosmos is yours to explore. In the sidebar there is a description of some of the telescopes I bought and used over the years, ranging in price from about $30 to $3,000.